third year students, how are you doing? Today in complex analysis we will be discussing about analytic function. For your information, the class I am taking today is the last one for complex differentiation portion. In the next class, hopefully, we will be continuing complex integration portion. So this is the last class for complex differentiation portion. In previous class, we discussed about the formation of complex function, the formation of analytic function. We used Milne-Thomson method how to construct an analytic function, which is the most prominent one. So today we will see an analytic function with constant modulus is always constant. I repeat it. An analytic function with constant modulus is always constant. So let us solve this. Firstly, we consider a complex function. So let us consider a complex function which is fz, which can be expressed as fz is equal to u plus I. You know, u is the real part and v is the imaginary part. U is the function of xy and v is the function of xy as well. So this is the complex function we considered at the onset. And now, so according to the proposition or according to the theorem, an analytic function with constant modulus. So we need to consider the modulus of this analytic function or constant or complex function is constant. That is, modulus of fz is equal to c. C is the constant here. An analytic function with constant modulus is constant. So at first we have to consider the modulus of this complex function or analytic function is constant. That means the modulus of this function, so we can replace fz by u plus iv is equal to c. C is the constant. So we can write this square root u square plus v square is equal to c. This can be written u square plus v square is equal to c square. We know we have withdrawn the modulus here. So this is equation number 1. Now differentiating equation number 1 partially with respect to x and y we get. So differentiating equation 1 partially with respect to x and y respectively, we get what? So by differentiating equation number 1 with respect to x, we get 2u del u by del x, 2v del v by del x is equal to 0. Since c square is the constant, so it is 0. We can write this u del u by del x plus v del v by del x is equal to 0. We can say this is equation number 2. And by differentiating partially equation number 1 with respect to y, we can write the same process: 2u del u by del y, 2v del v by del y is equal to 0, and this can be written u del u by del y, v del v by del y is equal to 0. So this is equation number 3. And from the Cauchy-Riemann equation about analytic function, we know from CR equation, CR means Cauchy-Riemann equation, we know del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. So by using the Cauchy-Riemann equation, we know del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. You know these four partial derivative of u and v with respect to x and y. These four partial derivative with respect to x and y, that is del u by del x, del v by del y, and del u by del y, del v by del x, satisfy the CR equation. So according to CR equation, we know this. So by using this CR equation, equation number 2 can be written as by using CR equation, we can write down the equation number 2 becomes u del u by del x can be replaced by del v by del y, and v del u by del y, we can replace this minus v, we can write this del u, minus del u by del y. You see, del u by del x is replaced by del u by del x is replaced by del v by del y, and del v by del x is replaced by here minus del u by del y. So this is equal to 0. So let us consider this as equation number, we can say this equation number 4. Okay. Equation number 3. We can write down this. We can use this. See, let us have a correction. By using this CR equation, we can write equation number 3. Say 3 becomes u del u by del y is equal to minus del v by del x. So minus u del v by del x plus v del u by del x is equal to 0. So this is equation number 4. Now squaring 2 and 3 and then adding. See, squaring 2 and equation number 4 and then adding, we can write down. You see, u del u by del x plus v del v by del x square plus this one minus u del u by del x plus v, this is del v del u by del x del u by del x square is equal to 0. So now we can write down, see, by simplifying we can write down this u square del u by del x whole square b square del v by del x whole square plus 2uv del u by del x del v by del x plus similarly u square del v by del x square plus 2uv, not plus, it should be v square del u by del x square minus 2uv del u by del x del v by del x is equal to 0. We can cancel these two terms here, and this implies, see, u square, we can easily write down this del u by del x square plus del v by del x square, v square, the same thing, del u by del x square and del v by del x square is equal to 0. And from these, this can be written u square plus v square del u by del x square plus del v by del x square is equal to 0. You know, you must not mix up these two things. Let me clarify. Del u by del x whole square and del square u by del x square, these two are not the same, so you need to be careful here. So this can be written, as we know, we considered initially fz is equal to u plus iv. So if we differentiate this with respect to x, I mean partial differentiation, we get f prime z is equal to del u by del x plus I del v by del x obviously, and if we take the modulus of f prime z, it becomes del u by del x plus I del v by del x. From these, by taking the modulus, so we can use the modulus formula here, del u by del x whole square plus del v by del x whole square, and mod f prime z square is equal to del u by del x square plus del v by del x square. So this portion can be replaced by modulus f prime z square. You see, mod f prime z square u square plus b square is equal to, this can be written c square, as you know, from equation number 1. So we can write down this here. Since c square is the constant, we can write down f prime z square is equal to 0. This implies f prime z is equal to 0. That means f prime z is equal to 0. And now by integrating this equation, we can write down fz is equal to c. So this implies an analytic function with constant modulus is constant. The analytic function with constant modulus is constant. Initially we considered the analytic function and its modulus is constant. So by using that we finally see the analytic function is constant as well. So this is the theorem we have proved today. Hopefully you go through this. This is very simple and easy. You can easily understand by learning this method. You are to go through the textbook, I mean the complex analysis or complex variables book as well. I prefer you to go through complex analysis by Shom's outline series. It is very useful for you, and you can follow some local author as well from Tita's series. As I said to you earlier, you can follow the complex analysis book authored by Professor Surajit sir. So you are to go through all these things about complex function, I mean analytic function. In the next class we will be discussing about complex integration. So till then, stay safe. Thank you.